are in listen-only mode.
Welcome all to this webinar about how you can use any building information model in finite element analysis. And this is a live event, so it means that if you have any questions, you can type them in the chat window, and I try to look them in the between. And if I miss the questions, I can come back to you after the webinar. But please use the chat window freely to ask anything about this topic. So this is a second of webinar series, and we are talking about prefab analysis, and this is about importing of those element walls. If you have made the elements in some other 3D software, it doesn't actually matter what software you're using, but if you have done modeling with the Revit or Tekla or any other software, how you can use those ready-made walls or any prefab systems in your finite element analysis. And we also talk about a bit like general finite element conversions. So if you are steel designer, you can use this information as well. So it's a general information. And we are all about the open building information models. So it means that we try to support as many ways to write 3D models in our software. And we also have dedicated links to our software. So it means that we have a dedicated link to Statica, Allplan, or Revit. But today we focus mostly on general BIM. So actually it doesn't matter what software you are using. We will try to support it as best as possible. And Arcos is our go-to contact for building information model things. So he has done many of these ideas what you will see today. And this is the content of today's presentation. So first we look what are the capabilities, then we look how we can import the IFC or any 3D model and make a finite element out of it. And then we learn how to fix those models to finite element without any references, and then we try to fix them with the master objects, which is like more powerful concept. And then we do some type conversions and first discuss how you can use those 3Ds as a references, and then we have question part if you have any further questions in the end. So this is a demo part. So first I just show how this works in general, and you can just follow, and then we learn how to do it afterwards. So the general problem is that usually those 3D models, they are volumetric models. So the walls have thicknesses and beam have the heights. And usually in finite element models, we want to use stick models and plates, what are called shells. So we want to flatten everything to the plane. And we have to simplify the model as well. So there's no any universal conversion. But if you can learn, this is not easy to do. And it's not, unfortunately, possible to automate. But if you learn to do this, the saving potential can be big. For small models, it can be like 4 hours worth of modeling, and if it's a big model, we can talk about the weeks worth of time savings per model. So this is the demonstration how the fixing of this, I would say this is a small model, but or medium-sized model, how this works. So we have imported the volumetric model. Then we use our correction tools. So we align the objects to masters, fix the floating point issues, and align the grid, connect objects together. And out comes the finite element model. And then we do some bigger corrections with the adjust analytical. And basically, roughly in 10 minutes or 5 minutes, this size model will be ready for finite element analysis. And we have simplified a pretty good finite element model. The second example, we import this model to finite element software. So we use IFC beams and IFC plates to import this structure. Then we just can convert those beams to shell models, and then we can connect those shells together and stretch to our master objects, and then we are done, and we can already run analysis because we can achieve the really good high quality mesh. So anything can be imported. This is a steel, but same applies to anything made out of concrete. And the third example is a steel building. So we have imported steel, but this can be equally well like concrete beam model or stick model. So there's nothing connected basically in the model. They are roughly in the right place. So that usually happens when you import the 3D model. And if we use those masters, we can make a pretty good finite element model, right? Almost like automatically. Only thing you have to tell the software where the masters are located. And pretty easily you get like really high quality model out of anything. You just have sticks in the 3D and then you use masters to connect them. And it's a really handy way to make a model. So first we discuss how you can import the model before we start to fix it. And this is the first part always. So we have an IFC model, which will include entities like IFC stairs, IFC spaces. We have building element proxies, which are non-load bearing entities usually. And then we have a beams, columns, which will be used usually in load bearing analysis, and also like in element frames, the walls and plates and so on. Then we open our software, we can read it in, and we can also read some of the objects as a solids or reference solids. And one of those objects like beams, they already have like dedicated type inside of the software. And we can also export them out of the software, even the rebars. So how it works? We just go to the file and open. And after that, the only thing you need to do is specify the file type as IFC. So if your software can write IFC files properly, we can import it. And then opens this dialog where there's a lot of like filtering. So let's discuss a bit about the filtering, because usually the problem in IFC is that there's so much information in the general IFC model. And the thing is that we have to get most of the data out of the model. And how we do it, we can filter by building on the left-hand side. Here is the building. Then we can filter by layers, and we can filter by element types. So probably if we are doing prefab analysis, maybe we just want IFC walls, if they are written correctly in the IFC wall class or type, and then we can use that. And we can also filter by size. I will explain later what that means. And we can also filter by load-bearing property. And it's also important to move the model close to origin. But let's first discuss how you can filter by building. So if you have many buildings inside of IFC, you can just select one. And if we desire to have the gray building, then we can just read that part of the IFC file. Second filtering type is by layer. So IFC has the layers, and we can select like any combination of layers to input as an analysis model. And finally, we have option to filter by story. So we can choose like story 1 to story 4, and that's what we need for finite element analysis. So probably want to story 5 as well, but anyway, we can filter. And this is also handy if you can classify in your software that what are the load-bearing elements, because IFC will include the load-bearing property. So we can classify which elements are load-bearing and which are not. And of course, we can classify the element type, like probably we only want walls and maybe beams and maybe columns, but maybe not plates or hollow cores. But it's up to you what you want to import. And by like making combination of these like filters, you can probably get your like biggest part of your finite element model there and get all the unnecessary parts out. So that's you can filter. And then you can filter by size. So examples of this, probably it's easier to see here by animation. So if we take like typical IFC and we filter by size, we can set the size to 0.3 meters. And then we can see what are the unnecessary elements, like the red ones, what will be taken out in the IFC file. There's a lot of like steel plates and growth of concrete and things like that. And if we put the size to 1 meter, we also can get rid of the foundations or like even small beams and things like that to only get walls. So also the size can be like a classification filter. And same here, if you look this steel model, we can classify by the size. So you can if we set the size to 20 centimeters, you can see that probably only the small details will be disappear. And if you put the size to bit bigger, let's say like 1 meter, it means that even small beams will go away. So you only get like main load bearing members in your concrete model. You set the size to 1 meter. So far, have you any questions? If not, we can then continue. But if you have anything, you can put it in the chat. So the main goal in this stage is to get the right information to finite element model and get most of the elements with the right type. If there's a wrong type, we can handle with the conversions later. And then, of course, it's important that the element is close to the origin, because we do a lot of multiplications in the finite element analysis. And that you lose accuracy when you do like 1,000 multiplications of big numbers. So we roughly want like same magnitude numbers in finite element analysis. So now we start to fixing, like this first part is really obvious and easy. It's just you learn it like really quickly what to do and what is the best strategy and how do you filter by story and layers. So first we fixing without references, and this is our goal. So we want to like simplify the model. One same like here, you get the idea. So we want to simplify the model as much as possible. So we have basically two buttons to fix building information models. And first is called adjust analytical model, and we looked at first. So there's few limitations. Elements has to be parallel, and it cannot destroy edges, and it cannot move on the walls in the depth direction, and it cannot work if there's a decimal issues or floating point issues like small deviations from the accurate model. And the second one, what we look later, will also handle if you have a decimal issues and small deviations. But let's look first the adjust analytical model, which will work for small models. And it's like about the correcting without any master objects. But there's always like hierarchy, so you have to understand that even though there's no like any master objects in your process, there's still like you define it by selection. So what you select defines the hierarchy of the objects. But first we look concept, what is called physical alignment. And physical alignment means that it does not affect the analysis of finite element model. And the idea in our software is that the physical model can store the original location of the parts. And if you want to export the elements back to IFC, they are bring back to the original location. So how it works in our software is that each of object, it doesn't matter what it is, but for instance, we have a hollow core here. It has alignment. And you notice that it doesn't affect the analysis model at all. So you can set any location for. And if you write those hollow cores back to the data model, and same applies to here. The example is the column. Also, columns tool has the physical alignment button, so you can set like how they are located, the axes, but it does not affect the finite element model at all. And same applies to walls. So walls can be located anywhere in the axis, right hand side, left hand side, or any position. But here is important if you set the wall location that you uncheck this consider eccentricity, so it's not taken into account in the finite element analysis. And then the final tool is called physical extend. So you can make elements bigger in physical model, but in finite element models they remain in the original size. So it's like the now you see the corner detail. It's like correctly, and they can be set in any model, and still our like our finite element model will be like intact. So it's this cube button here what will set the extent. Is it shrink or getting bigger or smaller? But still the midline model is there. The finite element model is like original. So now we do the corrections of this small example model. So now we correct the model without any like master objects. So you can see now we have imported the IFC inside of the software. There's a lot of gaps, like the physical model is okay. So these are the present the right location of the physical objects. But if you look the analytical model, nothing is pretty much connected together. And I always recommend that if you have these hollow cores, or we call them profile plays, that you turn off the detailed model before you start fixing the model. Then we start the adjust analytical model tool, and first we do alignment. And because we don't have any masters, we have to set the master ourselves. And you notice that the first question is the master. So we right click on the wall. So this will be the master. And then we select all the objects which will be on the same plane as these master objects. So 4 will be corrected, but 2 not. And there's a text that this beam is not parallel to the plane. And same is here, the element is like rotated. And that is the weakness of this tool, that everything has to be on the same like direction as the reference. And also the distance from this column was so high. So you notice that there's like about 7 meter distance or 6 meters. So we have to set the higher tolerance to the reference object to make them also align to this plane. And now only 2 objects were not corrected, and there were those which were not in the same plane. And we basically repeat the same process for each plane what the model has. So let's say we want to use this column as a master, and everything else will be aligned to that one. And same here. And we do exactly the same process in other directions. So maybe we want to use this wall as a master, and then we align every other object in the model to that plane. And now everything is flat except the floors. So let's do that as well. So we set the floor as a master. And now we also have to consider the distance from the objects from the master. So that's why we put a really high tolerance. And then we just select which should be on the floor place. And then now everything also in the height wise are flat. But please notice that the floors has to be like perfectly horizontal. If not, it does not work. Then we can just connect those elements, so we can connect shell models together. So this is the tolerance, and we can basically select any set of elements, but you should be very considerate what you select, because it affects what you select. If you select too many, it doesn't know what to do. So it's a usually better strategy to select like small set of items where you align those elements together. Okay. And this is final. Okay, we select the wall and plate, and then it means that okay, the wall and the plate will be connected. Connecting those like beam objects, that is not that simple. So let's see what happens if we try to connect beams together. And this is also the weakness of the correcting without the masters. So you can see if we select just two, it works just fine. You probably guess what happens if you select just two elements. But it depends what you select here. You notice that if I select like this and this will happen. If I select this and this, a different alignment will happen. So it's that's basically the weakness when you do not have masters. So it depends what you select and what order, what happens in the correction. So there's no like absolute truth how to fix it. But otherwise, if the beams are there, it's like really easy to do. And you can see that finite element model works. So it's that's how you basically fix small models. But the only limitation here is that everything has to be on the same plane. So it's excellent technique for small models, and we don't need any masters, so masters can be set by just right-clicking on the master. And it does not allow out-of-plane deviation, so that is like the limitation here. And B models can have multiple intersections, as you noticed. That is like the downside of this technique. So it's a not optimal solution. So do you have any questions so far? Oh, there's one question. How we can deal with slab at a different level, like one slab is 50 milli above slab 2 and don't want to be in the same level. Then you actually have to put really low tolerance if you want to spare that 50 millimeter. Yeah, and we can connect them together. Actually, there's a line connection if you want to spare that 50 millimeter deviation, but usually 50 millimeters in big models is so small deviation, so it's reasonable to put them in the same plane. So, but probably if you look the next tool, the more complex correct operations, you notice that how we can either save the height difference between the plates or leave it at it is, and then we need some line connection or connecting objects between those plates. So we start to then fixing with the master objects, and this is much more powerful concept. So fixing with the master objects, we're using this correct model tool, and it will work any geometry basically, and it can destroy edges, and that's sorry, it cannot. So that's like one downfall of this tool, but it can rotate objects and move them and stretch them freely, so they don't have to be on the same plane, and they don't have to be parallel into the plane. So it works in any model, even like very low quality model. And first, usually step what we take is the simplification, and I always recommend that you have to do the simplification first. So this is our raw model. It has the element connections and also a lot of holes and thin parts, and we simplify it by this, that this is probably what we want our finite element model to look like. So what can go wrong in simplification? So if we try to simplify and there's a geometric deviations, if you look this lower edge here, there's a geometric deviation, so that will cause artifacts like here or like here. They are not parallel. And usually the problem is that these deviations are like 0.1 millimeter, really small, so they are not that easy to spot by naked eye as it here. And the one downfall is also this corner, so the corner does not work at all. So it does not understand that this is a small detail. But we have tools to remove these corner details as well. So I will show later how you can fix those corners. So now we have a faulty model, but we can use the adjust analytical instead to fix that one. So we just stretch them, and there's a tool in the adjust analytical which is like stretch between the stories. And we set the tolerance here, so it will we will fix those like small deviations in the bottom of the element. Or this is also like one of my favorite techniques. So if the model is really nasty like this one, it's difficult to fix. We can use the modify region command and just like cut part of the element out. And now it's easy to align with all the others when you just like take part. But usually these like problematic elements, they are just like one or two per big model, so you don't have to fix every model in your big building, only just like few. So you can just manually remove those problematic edges. So now we look how the in practice do the simplification process for this building frame. So here we are. The building has a lot of details like here, and we can now run our correct model tool. What was the second of those tool sets, and then we run the fix small areas and lines command. And by tolerance, we can adjust what are the like smallest amount of detail what we want in our model. So by adjusting the tolerance, you can check that what happens. If we undo it and do it again with the like, let's try with the bigger tolerance and see what happens. So we put like 0.4 this time, and it even removes the small window. So you should always check what happens when you use this tool. So don't put like the whole model at once, because then you don't have any control what's going on in your simplification process. So it's a good idea to always like look what happens. Of course, you can do it for the whole building. Like here, if I put too high tolerance, it will remove like pretty much everything. So maybe that is something we don't want. But let's like try. Let's put it for the whole model, and like let's use like 0.3 for this model or this wall. But the best strategy is this go story by story or model by model. And here you can see the example of the problems. But in reality, those deviances are much smaller. So you can see that now there's like a small like angle in the or the corner, extra corner point in the wall. But we can fix that later. It's not that important. If we have those, they can be easily fixed later. And also you can see what happens with this wall if we try to, or this cast inside part of the plate. So be careful what happens there. So it will that's what happens if you try to simplify to sharp like triangles. So as you can see, you can run it for the whole building, but please check that what happens. So it's up to you what happens, and check it by element or story by story. So you get some kind of control what happens. So this is how you set your masters. So first we have to talk about those masters. So this is the optimal solution if you want to align anything with the bigger than like 10 elements. So we have three types of masters. We have axes, then we have stories, and then we have reference planes. And the difference between the story and reference plane means that reference plane can be anything. It can be any orientation. So and can be also smaller, like we have drawn in the lower chord connections. And this is what happens if we use those masters to align the objects. So this is the original and fixed, and original and fixed. And now we achieve the ultimate goal that there's like single connection point of those truss elements with the masters. So we set the roof plane and lower chord plane, and then we set those masters for. So we kind of hint to the computer where the ultimate location for the connection might be. And we can also use like if elements are out of plane, we can also fix that one with the masters. So those like planes will be the masters. And there's few strategies how to set those masters. So first problem is this one on the left-hand side. You set your master to end exactly at the object, and that is not optimal. The best way is this, because if you have like a thousand of millimeter deviation, it might be that this object is not fixed at all. So it's better to like extend those axes a bit beyond the object. Then if you set intersection points of those axes, you have to be really careful if they are not in the 90-degree angle. So it means that there's like three different intersections can be found in this. So they always should match in the same point or meet at the same point. So be really careful when you like put the angled axes that they meet in the single points. Otherwise, you will be in big trouble when you try to fix your model. And if you're using planes, it's even more difficult, because then you can find like 8 intersections in one point. That's difficult. Axis is also can be too long or too big. So if you have like two elements and you should want to spare the original location, you should use two axes. And it's even better if you make bit like small axes, two small axes. So now this element will not be like corrected with the other axis. So there's too few axes, and this is probably like better way that you set like two separate axes if you want to spare the original location. Same if you have like plates with the different elevation, like half meter difference, then you want to have like two stories next to each other. And this is usually what I don't recommend. This will work, but you have to be really careful when you're doing inclined planes, especially those intersections. So if you don't know what to do, this is not the thing you want to start with. So please do not use those angle planes. So let's see what happens in reality if you want to fix this model. So this model has a lot of like geometric, inconsistencies. And let's first put those axes. So we will put the stories. So the stories are really easy to put and fast way to put if you want to have anything in the horizontal plane. So basically, I just set few stories here and set the height, and the ground story or the basement has bit higher height, and there you go. It's pretty easy to fill as a table, or you can also set them by selecting plates, and always move the storage system so that your IFC building is inside of the storage system. Then we set axes. And now you think that, okay, this is like waste of time to draw some extra axes, but usually making axes like even like medium-sized buildings shouldn't take more than like 4 minutes or 5 minutes. And if you can save like let's say 8 hours of modeling, it's totally worth to define few axes. And my favorite way to define axes is by copying. You just make one axis and then you just copy it, and it's really fast to put like one direction axes in your model if you copy axes. So basically, I would say that like this element prefab frames, the making of axis system shouldn't take more than 5 minutes. And this is the example of reference plane. You can see that it's basically it can be in any orientation. You can even rotate those or stretch those planes afterwards. So we can rotate that and put it on the final place. But there you have to be really careful that they are on the right location when it's an inclined plane. So now we are ready to align everything, these masters. So you can notice that I have put intentionally like bigger deviations in the model, but in reality, those deviations can be like really small, like thousands of millimeters or something, like floating point issues. But here you can see the idea when I've made those like deviations much bigger, so you can see what's going on here. So let's try to now use the correct model and then try to fix this model. So I usually start by aligning everything to grid, and that means that it makes everything flat. So after this operation, if I align everything to grid, it still looks that it's not okay, but now everything is flat, like the stories are completely flat, and also wall lines are completely flat. So it's a good starting point for further fixing of the model. Okay, so at least the out of plane like decimal issues has now gone away. So let's do the stretch the structure grid. So that is the next operation, and that will take the corner points of any corner points of the walls and the beams, and it will fit them to the closest master or master crossing. And you can see that almost like biggest part of the model is now in good shape. But we noticed that, okay, there's a few points where the software hasn't fixed anything. Like this is one example, and this is one example. And the problem is that it was unable to correct because there were some parts of the elements that was beyond smaller than 30 centimeters. But then what happens, this edge goes to the zero, and that's not allowed, like the connection at the line B. But if we give it a hint, okay, let's make this distance smaller and try to fix the same element with the smaller tolerance. Same applies to this wall. If we try to move the corner point a bit closer to the desired location, and now we try to do the correct model again. Okay, let's try it again. You see, now it finds the right intersection, and same applies to the like this wall. If you try to with the smaller tolerance, so it totally makes sense that you have to fix the same model with multiple different tolerances, because if element has a really fine details, you have to use finer tolerance. If the element has only like it doesn't have any windows or anything, you can actually fix it by like a really big tolerance. I will explain later what is the problem here, but you have to understand that if there's any small details, this will not work. And you can see now almost all of the model is done, but we have one plate. This plate is okay, this is okay, but this one casting side plate is not aligned correctly. And we try to stretch it, but nothing happens, the gap remains. So now we have to open it in the separate view to understand what happens. And you can see that it's not aligned. And what is the issue here? By the way, I always like that you see those corner points. You can see that there's a corner points, but it's a good technique that if you go to the settings of software and then set like in the CAD objects part of the display, you set the corner points visible, so you can see small dot where there's a corner point. And this small corner point is the issue. So both of those corner points will be stretched to the same master reference place. So if you move it this corner point a bit further away from the corner, it probably works. And here it's the same issue. We have two corner points really close to each other. So we move it here, and let's now try to fix it. Because the problem was that it didn't know what to do. There was two corner points, and you have to go all of these corner points in the element to understand what is the issue, why it doesn't want to fix it. And now it works. You can see now it's a perfect model. So now everything should be connected. So what can go wrong if you think about that the red dots will present the tolerance? So if this is how you think it, that this is like you just look the corner points and I want to stretch these. But in reality, computer sees there's like a lot of corner points. So it, for instance, like this window cannot stretch here, so that is not allowed. Or this opening here will go to the corner, or this extra corner point. So always you have to look all of those corner points to understand why the fixing is not working. And try to decrease the tolerance or remove small details or divide the element to solve this issue or move corner points to make it work. And final touch to make this model work is filling the big gaps and removal of the extra nodes. So let's look at that one. That's pretty simple. So if you look the basement level of this model, there's like very high beams, and that's really typical for the basement models that you have a really high load bearing beams. And that's why you can use adjust analytical model, and then we just align, but we can use really big tolerance for all the objects here, like 0.9 meter. So now all the load bearing beams will be same plane as the floor plate, and we can also stretch between the stories. So we select stretch between the stories with the 1 meter tolerance, and we can also fix the columns to make them exactly the story height in the basement level. And that is usually needed when you have a parking decks or something like that. You have really high beams, so you have to fix. And then we have also these beam gaps here, so we want to fit those. And the fit between the stories is perfect tool to fix those as well. So we select by story, and we set the really high tolerance, let's say like 1.5 meters, and now it will be gone like here. And also there, so the edge will be stretched to the story level, and now they are gone. So it's a handy if you have a big model, you can fix like 30 walls in just like 1 second. And we can probably run it for the whole model because it's a pretty safe operation. Usually it doesn't do any harm here. So basically that's, we should have like almost perfect model, except those corner points. So we want to remove, because each of those finite elements have to follow these corner points, and that can be like a problem. So we just select the operation which is called like merge region lines. So if we have extra points, we can use this operation to remove the extra lines in the model. So the model is almost like done, and we can try to make the finite element model. And the quality of mesh is like pretty good. So that's how you basically do it. So by the way, do you have any questions so far? There's no questions, so we can continue. Good. Then the final thing I want to talk about is type conversions, because not everything comes inside to the finite element software with the right type. So let's say that we have roughly the walls come as a walls, but we might have problems. for instance, we have hollow cores, which might be on the wrong type. And there's a good thing that we can convert anything also inside of the software to different type. For instance, if we have beams, we can convert them to the hollow cores, or if we have like walls, we can convert them to the beams. So let's see what that means. So here is the typical model. If we have imported hollow cores to the FEM-Design, what happens is usually software write those hollow cores as a beam, and that is not, most of the cases, that is not the desired analytical model. So we take the profile plate command and we can convert any of those hollow core beams to shell models. But now they are individual shell models, so that is not actually what we want. So see what happens if I select the whole floor, and if they are touching each other, like here, most of the time, or most of the model, it works. But there's one connection, so we can use correct model to connect these two elements together. So there's a command called stretch regions in plane. But first we have to align everything to plane to make this work. And then we can use modify region, and then we can just like connect them to go together like this. Now it's a single hollow core. But like this model, it would be also really quick to draw. Just import the walls with the IFC and then just like... But it's possible. And this is the borderline case, if this is even reasonable. If you look like this model, it's not so obvious that is it reasonable, because now they are beam, and beam doesn't have any like angled end or inclined end. So the problem is that if we convert those, and by the way, first align everything to the plane, otherwise it doesn't work. So we have to use correct model before you use this one. And then we have to, of course, cut it like this. And then you can just like a normal way use those alignment tools to align everything together. But it's possible, but then you have to understand that is it even like worthwhile to do. So it's probably faster to draw those hollow cores just by like inputting 4 corner points yourself and with the hollow core command. So maybe it's worthwhile to just like import the walls and do not forget about the hollow cores at all. And always use align to grid before you start this hollow core importing process, because otherwise this tool doesn't work. They have to be perfectly in the same plane otherwise they are not connected. Okay. And this is the other example what you can do with the type conversion. So here we want to design foundations of this building. So we have imported IFC model inside the finite element software. And on the first glance, this look like fine. But if you looked at what has happened here, this is actually wall. This is wall. This is not what we want, and this is wall. So now we have to convert those element types. And the foundations are beams. So I don't know if that's what you want. If you don't want beam, maybe you want to have a slab. So you can use foundation, wall foundation command, because you can convert any beam to the wall foundation. And with the wall foundation, the shell models are created automatically, because with the wall foundation, you can set the type of the wall foundation to plate. So we can convert almost anything to any type. So let's set the surface support. So it means that now with the shell model, so now we actually have what we want. And if you have a piling plate, you can convert them to the normal plates. So you can set your pile split like offset. Then we have this one element here and these elements which are not correct. How do we handle these? So we can try to open the plain plate command and try to convert these IFC objects to plate and see what happens. But that is basically what we don't want. Now it's like vertical. So how we can fix this one? So let's go back to the wall model and see what happens if you first convert these to beams. So now they are beam. And you probably guess what happens now if you try to convert them back to the plate. So we take the plane command and convert them, and now they are what we want. So we actually get the foundation geometry automatically from the IFC model. We just need some conversions to do that, and now we can convert them to foundation slabs, so that also has a support there. Then we notice that we have like these beams, actually columns, but they are walls. So we can open just the column command and convert them to columns automatically. And same applies to these IFC beams, so we can convert them to beam. And the final, like really difficult part in the model is this mid support there. So how we do that one? That is like hard to do. If you're trying to do the beam, you can see it doesn't work. So that is not what we want. We want something else. We want to have the wall part and the foundation part of that wall. But what we can convert it to, to plate, and even that doesn't work. So what we do? If you have anything like this, that it's really problematic, like the 3D model is correct, but you cannot convert it to anything meaningful, you can use tool which is called like solid. So you draw solid like here, and you can convert it to solid. So this is a new feature what comes to the next version of FEM-Design. So now it's a three-dimensional solid. So now you can use any face of this solid to create analytical objects. So you can make a plate. So I can convert like one region, or make a plate with this like solid bottom plate or bottom face. So there you have your plate, and there have your vertical part. So eventually we get what we want out of this 3D block. We just need to be like clever. So make it first like solid, and then we get everything out. And here you continue as usual. You just align everything together. And of course we can make it a foundation plate, but you just align everything to axes and connect elements together, and then there you have it, almost what you want from this model. So by conversions you can do that one. And if you want to use, you have some like complex geometry and you want to use it in finite element analysis, you can import anything to the software as a reference solid, as the import dialog here says that you can set anything, even IFC walls or anything as a reference solid. So I can set the type here like this. Okay. And it's important, if you do the solids, that you also remember to uncheck this filtering by size. And you can also spare your original model as a solid. But let's see how we can use these. So now we have imported those solid objects inside of finite element model. They are here in the separate layer. And it's important that you check that it's open. Okay. And now we can do type conversions. So we can take the BIM command and try to convert those like volumetric objects to anything meaningful finite element objects. So we just right click here, and it try to guess or get the best shape out of the 3D model. So only thing we need to set now is the physical model, and after that we just align elements together. So as you can see, we can convert anything, or for the plates or flanges, probably want to use like plate command to make them as a shell models. So that's basically how you can use solids. Or you can even input the whole model as a solid. If you input like 3D solid in the finite element software, just open the layer, and then you can generate your finite element plates with the plane command, plane plate. So you can convert any solid to the plate like this. Or the other option would be that you can just use the corner points to snap the corner points of the solid. So you just use the pencil and draw the whole thing yourself. So you just click those corner points. So also that is like okay way to do it. So you just draw with the solid, and you pretty quickly get like your finite element model. The only thing is missing. We have to put the hole and fillet for the hole, but I just make a square hole here. And then all we need to do is to use those like correct model. So we stretch to these 4 references, and then we connect shell models together to make it work like here, like this one. Adjust analytical model and connect them together, and then we get like almost perfect like finite element model easily. It doesn't take long to do this. Any other uses of 3D references? So we also can make loads with the 3D objects what we can input as a solid. So if you have a plate like here and you want to define loads like really quickly, you can input your references, and I can also input IFC spaces here. And now if I define the loads, I go to surface load and I set the resultant of an area. I can really quickly define loads of my 3D model by importing those objects which will cause the load. Like they can be like these railings here, IFC railing. And you don't have to be exact when you're drawing these loads, because everything can be aligned afterwards, even the loads. So you just place the loads roughly where they need to be, and I can project them to the plate later. Like here, like let's say it's here and like here, and the final thing would be that I use the IFC space to create surface load. So maybe here is the most optimal way, is that just use those corner points to define the loading area. So IFC space is the class which defines the class what is used, like the live load class. And then we just use the correct model and cast every possible aligned to structure grid. So now the loads would be aligned to plate automatically. So the correct model also works for loading. So now it's on the plate. And there's other few uses. If you remember, put this setting in the beginning that you want to spare the original model as reference solids, what you can do with that one, it's really handy for element conversions. If you're doing like element frames like here. So now we have the original geometry still stored in the as IFCs. And if you forget it, you can paste file it afterwards. So we can compare the analytical model and the original geometry together, so we can see how much scene we have done here when we did the conversions. So like for instance, this wall, it was like we removed a lot of stuff. So it's really quick way to check that you have every possible column in your system and you haven't done anything stupid when you fixed your model. For instance, if you look like probably this one here, it's probably not reasonable to remove that part of the element, but you can see it like with the 3D model really easily if you just spare the original geometry. So do you have any questions? So I this was an idea that I just show you like introduction to this, that how you can fix this, and I like I told you, this is not easy, but like the saving potential is like so huge with this technique that if you can import elements and fix them here, you will save a lot of money and time. And if you want to have a training or like a individual help, you can always contact me if you have any questions about this thing. But do you have questions here if you want to ask anything? Okay, if you don't have any other questions, at least let's look at the chat. There's not any questions. Then we can end. But if you have any questions, please contact me afterwards. And this will be uploaded to YouTube. So if this was too fast, maybe you can look it there. It's a bit slower and easier to look there. I thank you all, and let's hope to see you next webinar.